University, and my advisor is Dr. Parkin, and today I'm going to talk to you about uridine nucleoside hydrolase and its substrate analogs. So you guys have an idea about the direction that I plan on taking my talk in. I'm going to tell you my research question. So, what is the effect of the 2'-OH group of ribose on the catalytic strategy of uridine nucleoside hydrolase in complex with uridine substrate analogs? I'm going to present you with background information on our enzyme, on nucleoside hydrolases. Our enzyme comes from the nucleoside hydrolase superfamily. Now, research has been done in the past on these enzymes. There are non-specific enzymes, for example, that catalyze both the purine and pyrimidine nucleosides, such as IUNH, and there's slightly more specific ones, for example, maybe CUNH, that catalyze only pyrimidines, cytosine and uridine. Our enzyme is a nucleoside hydrolase, as mentioned in our research question slide, called uridine nucleoside hydrolase. Now, here's the least specific enzyme. This is inosine uridine nucleoside hydrolase. Now, this enzyme can cleave the N-glycosidic bonds of all of these nucleosides, which is uridine, adenosine, inosine, guanosine, and cytosine. Now, I bring you next to the most specific nucleoside hydrolase, the enzyme I've been working with, known as uridine nucleoside hydrolase, and it only cleaves the N-glycosidic bond of this nucleoside uridine. Now, why is our enzyme unique? Well, as mentioned before, it cleaves only one nucleoside efficiently, and in the superfamily of enzymes, I also mentioned some are more specific than others. However, ours is the most specific, and our enzyme, most importantly, exists in the parasite Trichomonas vaginalis. Now, here's the N-ribohydrolase reaction done in our lab. Just imagine our enzyme, uridine nucleoside hydrolase. This N-glycosidic bond is cleaved by an SM1 type mechanism, and ribose and uracil are formed. Now, originally we wanted to see if the 2'-OH group affected the catalytic strategy, so we decided to compare two substrates, uridine and thymidine. And as you notice here, uridine has a 2'-OH group, and thymidine doesn't. However, uridine has a rate constant of about 10,000 times greater than thymidine. So, to summarize these findings, the rate constant is 10,000 times greater, and this is due to the 2'-OH group on uridine. And finding out the rates of a reaction with our enzyme, finding out the rates of reaction of different substrates with our enzyme could eventually help us design an inhibitor, potentially killing the parasite Trichomonas. However, we made an assumption too quickly. Thymidine contains a methyl group, and uridine does not. See, that's uridine. It doesn't contain a methyl group, and thymidine does. So, we decided to bring another substrate analog into the picture. This is known as 5-methyluridine. It has a 2'-OH group and a methyl group. I'm going to give you some basic terminology so that way when you're presented with my data, you'll have a much clearer understanding. Now, Vmax affects catalysis, and Km or Ks affects binding, and these are our analogs, uridine, 5-methyluridine, and thymidine. Uridine has a 2'-OH group, as mentioned before. 5-methyluridine has both a 2'-OH group and a 5-methyl group. And thymidine only has the 5-methyl group and no 2'-OH group. Okay, before I show you the data, I'll give you a brief analysis on our analogs. Uridine is our control because it is naturally occurring and contains a number of substrate analogs. The substrate analogs 5-methyluridine and thymidine are used to see if the 2'-OH group bound to uridine affects the reaction rate. In order to see if the 2'-OH group bound to uridine affects the catalytic strategy of UNH, we must compare uridine to thymidine. However, thymidine does contain that methyl group. So, we must compare 5-methyluridine to uridine before comparing uridine to thymidine to see what effect the methyl group has on the reaction rate. And here is our most important finding. Now, if you look at this data, this is Vmax and this is the catalytic factors. As you can see, between each substrate, there's a big difference in the Vmax or the catalysis. And if you look at the Km, this is binding. Now, as you can see, there's not such a big difference between uridine and 5-methyluridine binding-wise, but there's a big difference between 5-methyluridine and thymidine binding-wise. And basically, the higher the number, the lower the binding affinity the substrate has to the enzyme. And V on K is the catalytic efficiency. So as you can see, uridine has a much higher catalytic efficiency when bound to uridine nucleoside hydrolase than 5-methyluridine and thymidine. Okay, so I'm going to summarize what you saw. There is a large difference between 5-methyluridine and thymidine catalytically because there's a large difference between their Vmax values. The large difference between the Vmax values of uridine and 5-methyluridine affects catalysis. There's a large difference between Km and Ks of thymidine and 5-methyluridine, and that affects binding. The large difference between the Vmax of thymidine and uridine, thymidine and 5-methyluridine affects catalysis. Most importantly, there's a large difference between the Km and Vmax of thymidine and uridine. Okay, so I'm going to go through the dissociation constants and inhibition. As you know, you might have noticed in my data slide that I put down Km and Ks. Well, 5-methyluridine and thymidine, the Km is also a dissociation constant because they act like inhibitors because they have a lower reaction rate than uridine, but they still react with UNH. They're just not as efficient with catalysis or binding. And since they act as inhibitors, the Km is equivalent to the Ks, and Ks is considered a dissociation constant because we're seeing the effect of binding with the 2'-OH group and the 5-methyl group. I'm going to give you a comparison on catalytic efficiency. I decided to compare catalytic efficiency differences because the 2'-OH group affects both Vmax catalysis and Km-Ks binding. Okay, so here we have 5-methyluridine and uridine. Its catalytic efficiency difference, delta G, is 9.1 kilojoules per mole. But if you look at thymidine and 5-methyluridine, the delta G is 32.3 kilojoules per mole. But if you look at the biggest difference between thymidine and uridine, the delta G is 41.9 kilojoules per mole. And I'm going to give you an explanation on the catalytic efficiency comparison. So, here, as you can see, the delta G's for thymidine and 5-methyluridine and uridine and 5-methyluridine add to about the delta G for thymidine and uridine. This shows that there are no synergistic effects between the comparison of the 2'OH group and the methyl group. If there were synergistic effects, it would have possibly been higher, like maybe 60, for example. So we use the V on K because we cannot compare the binding difference of 2'OH directly because, as mentioned before, the 2'OH group affects both Km and Vmax. So, therefore, we can conclude that the 2'OH group affects catalysis and binding, and the 5-methyl group only affects catalysis. So, I wanted to compare how our data is different from prior data. So we're going to start with another nucleoside hydrolase called inosine adenosine guanosine nucleoside hydrolase, and it cleaves the purines, inosine, adenosine, and guanosine. So, a comparison was done between 2,3' and 5' dioxyadenosine as compared to adenosine using this enzyme IAG nucleoside hydrolase. The 2'OH group on adenosine affected catalysis, but it had a very small effect on binding. Now this is different than the 2'OH group on uridine with uridine nucleoside hydrolase. Our enzyme that we use, uridine nucleoside hydrolase, is very specific. And until recently, only 4 classes of these nucleoside hydrolases were catalyzed. The non-specific IUNHs, which I mentioned in the beginning of the talk, the IGNH, the IAG, and the GINHs, and the pure pyrimidine specific, which are the closest to ours, the cytosine uridine nucleoside hydrolases. Now, we decided to compare an enzyme that's more closely related to ours, the cytosine uridine nucleoside hydrolase. And it's more closely related to ours because it's more specific than the other ones. For example, this one cleaves uridine and cytosine, so it only cleaves 2 nucleobases. Ours only cleaves 1 nucleobase, so so this one's specific but not as specific as ours. And prior data does not contain anything relating to the catalytic strategy. However, there is a lot of X-ray crystallography data, so a lot has been done in that field. And our future goal is we want to try to work with more substrates so we can compare the catalytic strategy of our enzyme with other substrates. And we want to eventually figure out a mechanism between our enzyme and its active site. Therefore, if we figure out this mechanism, we could potentially design an inhibitor. And here's basically a sample of our goal. This is the prospective active site cartoon. And this is our substrate, so it would be uridine. And this blue part is our enzyme. And we want to find out the interaction so we could eventually design an inhibitor and potentially kill this parasite. So we're excited, and I would like to thank Dr. Parkin for advising me on my research and helping me reach my goals. I would like to thank everyone for their time and attention and any questions.